All right, so our final exam is not really comprehensive. It is on volcanoes. However, there's earthquakes when we have volcanoes, right? And we only find volcanoes at certain plate boundaries. So you have to understand a little bit about all of those things, which is why we wait for volcanoes for the very end, right? So what I'm going to do is go through the review that I posted on Canvas, and then at the end, if you guys have additional questions that I haven't answered, you guys can ask them then. Sound good? Cool. Now, when we talk about volcanoes, we have to talk about magma, right? Liquid rock, and how magma forms. And for this, we need two diagrams, right? Does anybody remember what one way magma forms? How you turn rock into liquid magma?
Pressure.
Pressure, right? You lower the pressure, decompression melting. Turns mantle into magma. So, here we have a spreading center. What type of plate boundary do we call this? Divergent. We have our mantle. And somehow we're creating this liquid magma. What is it called when it reaches the surface?
Lava.
Lava. Right? And just the action of opening up the crust decompresses your system, which causes a change in your mantle to melt into magma. Pretty simple thing. You guys remember this demonstration, right? The music helped. So remember the syringe demonstration, where I boiled water with my bare hands in a syringe, and that was it. And it was awesome. It was cool. Typically, when we talk about the composition of the mantle, right, so now we're thinking periodic table of elements, composition. What are some elements that you'll find in magma at a spreading center? Iron. Magnesium. There's silica and oxygen. Right? That's why you see this. The whole reason this is dark is because there's a bunch of iron, a bunch of magnesium. These are the elements that you're going to find at our spreading center, divergent, boundary, that sort of thing. Now, what type of volcanoes are you going to expect here?
Shield.
Yeah, we're going to expect our shield volcanoes because it's low in silica, so it's very viscous, so it flows really easily. If it's on the continent, what kind of volcano might we expect? A cone, a cinder cone. Right? We're currently extending the basin and range, which means that most of central Utah has cinder cones, and it's associated with us rifting the crust apart. We also have a few small shield volcanoes in Utah as well. All right, what is the next way that I can make magma? Thank you. We call this dehydration melting. All right, so we've got oceanic crust, continental crust, fishies. How does dehydration melting occur?
water is dragged along with the going down oceanic crust.
Yeah. As we subduct our crust, we're cracking it. Water's filling in the cracks. And there's water in the minerals in this rock. In the actual atomic structure of this rock, there is water. It's in there pretty good. But, oh no! I broke it into several pieces. You should see me terraform in half. Yeah, so we add heat. So we're adding heat. Heat coming from radioactive decay. Heat coming from the leftover heat from the formation of our planet. Right? So we heat this up, drive the water into the mantle. When you put water into mantle, it lowers the melting temperature. And you get magma. H2O plus mantle equals lower melting temperature equals magma. Beautiful. Laws of physics, right? Now, we know that when you melt mantle, you have iron and magnesium. So that's what we're going to find down here. But by the time the magma gets up here, it has a completely different chemistry, doesn't it? What one element does it specifically have more of by the time it reaches here? Silicon. Right? Lots and lots of silicon, which means we have lots and lots of explosions in the form of our composite volcanoes. We'll also have a lot of calcium, sodium, and potassium. And we call this either felsic or intermediate. Whereas over here, we call this mafic. Right? But if we look at all these rocks strewn across this table, which probably hasn't been cleaned in 30 years, we notice that some of the magma has different colors, there's different minerals in there, which means it's changed the composition. So now we know how to melt rock, we know how to melt mantle, we know how to melt rock and turn it into liquid rock. Now we need to figure out how to change the composition. How do we get from a mafic-rich magma below our volcanic arc at a subduction zone into felsic or intermediate composition at the top? So a change in magma composition. Dog? A person? Sorry, Davis campus, but totally yesterday I was sitting in bed, because I'm supposed to lay down when I'm at home, and I have a doorbell in our garage down in the basement because it was added on. Totally rang. Which means somebody had to have gotten into the garage, like, I don't know how, and rang the doorbell. My husband convinced me it was an electrical charge, but holy moly, when you're by yourself, and you're injured and you're like, what was that? Weird sound. Anyways, changes in magma composition. There are 3 ways that we can do this. Does anybody know one of them?
Yes. As the magma rises, because it becomes less dense when it melts, it also melts the stuff that it's going through and grabs onto that and incorporates it into the magma.
Yeah, so that's our magma assimilation. Yeah.
So when the magma cools in temperature, more mafic components cool at a higher temperature.
Yes. So that is our magma, or magmatic differentiation. And our final one is our magma mixing. Now, this one you guys should be familiar with because remember at the beginning of the semester I said you're honorary scientists? Yeah. Now you're real scientists, right? I've convinced you to become geologists. I've assimilated you into the geologist field. No? That's a good thought. It was a good thought. All right, yes, so we have magmatic differentiation. Biggest thing is we're starting to cool the magma. And because of Bowen's reaction series, right, stuff that's heavy in iron will start to crystallize first. It will fall out of the magma, which will leave the magma depleted in iron now. Or richer in silica, right? So our magmatic differentiation, assimilation. Oops. I love that you said density because density controls this entire thing, right? The density of the atoms controls this. So as this is rising, it's surrounded by our country rock, which say is felsic, so rich in silica. Say this is mafic, but it's hot. And if you start to heat up felsic material, it'll start to melt and go into our magma and change it. It's not felsic, it's not mafic, it changes it to intermediate composition. Fantastic, and this is happening kilometers below the surface of the Earth. It takes thousands to millions of years to do. But it changes our composition. And then we have our magma mixing. So say we have a felsic magma sitting here. He's kind of upset. Nobody wants to hang out with him. Then we have this mafic magma that's like, hey, this is great. I'm like really close to this other guy. I'm going to go say hi. Right? Because he's a whole lot hotter than this guy. So he's rising. This guy's kind of just stagnant, which is also why he's kind of sad. So this guy meets up with this guy, add them together, and you get intermediate, or somehow you change your chemical composition of the magma.
Question.
Yeah.
So the two groups of magma in close proximity like that, are they from the same magmic chamber that is rising? Or?
Not necessarily. It's very complicated, and we don't necessarily completely understand all that goes into it, right? Because it depends on where the magma is being generated. If it's a subduction zone, and remember when the Farallon plate went under the North American continent, we were subducting the spreading center. Well, that has a different chemistry than if you're just subducting a slab. And along the slab, right, you might subduct an island, which has a different chemical composition. But they're melting right next to each other. So,
Okay.
yeah, it gets really complicated really quickly. Yes, okay, so changes in magma composition. What I just erased included the two main types of plate boundaries, which was our divergent plate boundary and our convergent plate boundary. You guys just got done reviewing the Yellowstone hotspot and understanding its mantle plume ability. So if you guys have trouble with that, come see me. We can talk about it. I'm not going to review that specifically. We drew it all up in that diagram, but it's just know the different plate tectonic processes and which volcanoes form at each, which we just labeled, which I just erased. So we already wrote it down. All right. Now we want to go over our volcanic hazards. We're going to list them off in order of, well, at least the first three in order of deadliness, right? So our most deadly volcanic hazard is hands down our pyroclastic flow. It can get up to 1300 degrees C, and it can move as much as 400 miles per hour. Generally, it ranges between 125 and 400 miles an hour. It's still faster than you can run, so, you know, might as well know the extremes so you can make other people's jaws drop. All right, the next one is our tsunami. Right, you have an explosion underwater, you displace the water, creating a tsunami. These are specifically related to things around the Ring of Fire. That's where we have a lot of tsunami-related hazards. And then we have our climate change, which can lead to famine. We're adding a bunch of sulfur dioxide to the air, carbon dioxide to the air. That can warm things up. We're also adding a bunch of ash to the air. That can cool things down. So depending on how much of each is released into the atmosphere, it can result in famine. You're also covering the entire region with ash. Generally not so good for plants since you're covering them and whatnot. All right. Next thing we have is our lava flow. If you can't outrun a lava flow, you're generally doing something wrong. But it is a hazard if you can't move, right? If I was stuck in my wheelchair in the mud, I would have been in trouble, right? I'm crawling, army crawling. I probably still could have outrun it, army crawling. But that's a hazard. Our ash fall. It's a definite hazard. Your house cannot support 3 feet of ash. It's 3 feet of rock covering your entire roof. Not sustainable. As well, right, we know that microscopically, this is what ash looks like. If it gets into your lungs, it's shards of glass, which will cut you up. It also, if it's small pieces of pumice, if it gets into your lungs, there's water in your lungs, there's moisture, it fills those voids, makes a sticky paste, coats your lungs, and you suffocate. So, whenever you're in a volcanic eruption, please cover your mouth. Probably won't happen here in Utah, but if Yellowstone goes off and you happen to survive, put on a helmet and cover your mouth. It might. It might. Ron White, the comedian, I can't say because it's a bad word, but go look it up. Put on a helmet. Great. We have gases that are released. Specifically, we've got CO2 during the eruption, sulfur dioxide leading up to and during the eruption. You can get hydrogen sulfide. You can also get water vapor, plus a few others. Carbon dioxide is heavier than air. if you happen to be in a valley at night sleeping and carbon dioxide is released into that valley, you will suffocate. That's happened several times. Sulfur dioxide combines with elements in the air to create acid rain. Hydrogen sulfide, same thing. As well, carbon dioxide and water act as greenhouse gases, which can increase the temperature globally. Pyroclastic flows cannot increase global temperatures. Repeat that with me. Pyroclastic flows cannot increase global temperatures. Only local temperatures. Okay? What am I going to say about that? All right, then you can have flank collapse. We saw this with Mount St. Helens. Massive landslide decompresses your system, can cause an eruption, can cause a landslide, several things like that. Then we have our volcanic lightning. As a hazard. Now what I want you to keep in mind is Dante's Peak, which we're going to be watching on Monday, or you've already watched, has every single one of these.
Good job.
Yeah, it's fantastic.
The tsunami?
Okay, yeah. Dang it. Not the tsunami. But everything else. Why they built an overpass in the tiny town of Dante's Peak, though, and only have one road in and out of the town that's a bridge, and a dam, there's just, it's great. It's going to be great. Monday's going to be great. Oh, I forgot one of the most important ones. Oh my gosh. Lahar. Hot. Mud. Fast. Terrifying. Flying. Whatever.
Those are going to be the words on the test.
If you use that, I'll know what you mean, right? Then you know, I know that you've seen videos of a lahar coming hot, fast, muddy towards you, or towards somebody else that is in a very dangerous place. Right, lahar is made from melting snow. Somehow there's a lake up at the top of the volcanic eruption. That lake drains, the snow melts, incorporates all the mud on a steep flank, comes rushing down all of the drainage paths. Not a good day. You good? Yeah.
If there's a lake like near a volcano, would it become a Seiche effect?
If the earthquakes are strong enough.
Okay, not necessarily from the eruption.
No, it would be from the earthquake swarms. Yeah. How to predict? You guys are experts on this? Tell me, what are the ways to predict volcanic eruption?
Gas emissions.
Gas,
Deformation.
information,
Past history.
eruption history,
Heat. Temperature.
heat, temperature, earthquakes. Yes, beautiful. On Dante's Peak, the gas kills the trees, starts to kill the plants. The heat kills those poor swimmers at the very beginning. He talks about eruption history. They have seismometers and tilt meters measuring the size, and they have seismographs all over the mountain. So they do all the necessary steps required to predict if a volcanic eruption is coming, which now you guys can successfully do up in Yellowstone. Great. Don't forget your helmet. All right. One thing about these hazards and predicting, right? The hazard of an eruption cannot be controlled. The risk can, right? The hazard is there whether we're here or not. The risk can be controlled. First of all, just by stopping people from living around areas that have volcanic activity. If that turns off, can you let me know?
Yeah.
That's a 29-minute timer, so I have to... Yes, the risk can be controlled. But we also want to know that volcanoes aren't all bad. Right? We have some benefits. What's one of your favorite benefits of volcanoes?
New land.
Fertile soil.
Black sand beaches.
Black sand beaches, right? We've got islands, but because of that, right, the oceans and the atmosphere are breathable and sustainable because of volcanic activity in the past. We'd still be covered in 2 kilometers of ice if it wasn't for volcanic eruptions. So we like volcanoes. We like them for their materials. Zeolites are used to filter water. Sometimes we use volcanic materials for building materials. We use pumice to clean our feet at night. One of the most important ones, though, is our hydrothermal alteration. And why is that our favorite? Believe me, it's your favorite.
Energy.
Not quite. We'll get to energy. Hot springs. Does anybody here like gold and silver?
Oh, yeah.
Your phones, right? This is where we get all of our ore deposits. The richest concentration of ores is by our divergent plate boundaries, where the water is circulating through, concentrating elements like gold and silver and molybdenum, all the things that we love. And then we also have thermal energy. "200 wells up in the parking lot, several more wells down below social sciences. Weber State runs on geothermal energy. So does most of Iceland. But Weber State, right? The Wildcats.